right? Yeah, so let me just go over the step. For the record, we have y equal 130, x over 2, the same equation here. We apply logs to both sides, so we end up with log y, and we end up with log 130 x over 2, right? That's what we end up with. Then we, as someone said, we open the bracket or we apply our log law. We end up with log 130 plus log x3 over 2. We see another opportunity to apply our log laws. We bring over 3 over 2 and we end up with log y, log 130 plus 3 over 2 log x, right? So then we equate this now to our equation of a line, right? So our equation of a line is y equals c plus mx, or y equal mx plus c, doesn't really matter, plus sign, right? What is our c value?
Log 130.
Right, so that would be our c value, log 130. And what is our gradient?
3 over 2.
3 over 2.
Right, so our gradient is 3 over 2. And what is our x value?
Log x.
Right, log x is our x variable. So very easy stuff, right? Now we move on to finding the slope, right? After we got a we got this, yeah, we got this formula, right? Say we got a graph and we got some points on it. How would we find our slope? Remember slope or gradient? How do we calculate our slope or gradient? How do we calculate the slope or gradient? Anybody remember?
Repeat, sir.
What's the formula to find our gradient? Let me start you off. Y2
y2 minus y1 over x2 minus x1.
right? X2 minus x1. So if we had log y here, as we said, log y, and we had log x here, what would our formula look like for gradient? What would we, let's plug in our values, right? What would that look like? I'll start you off again. We have log y2. What's the next step? We have log y2, log y2 minus come on guys, it's not really hard, very easy, right? We have y2, y1. So we have y2 up here, y1, and down here we have x2, x1. All right, is that better? Y2, y1. Now what would we have here? We have log y2 minus what?
Minus log y1.
Log y1 over, what's the next step?
Log x2.
Log x2.
Log x2 minus log x1.
Right. So we're just applying, you'll see more of these in the future, right? But we're just applying logs as you said, not real. Some of us are not real doing pure maths or doing integrated mathematics. So we have to go through these just to ensure that we're not, or that we're familiar with it when the time comes. And it's the same thing we had here. The answer is here, right? It's the same thing down here. All right, so we'll move on now to measurements, right? We also have some basics to cover in measurements. We won't be able to finish it in the time. We won't be able to finish by 11:30. Remember that we'll come back after lunch again. And so we'll take a break and then we'll come back. But we'll look on measurements. So the first thing in measurements we have to look on is accuracy, right? And accuracy refers to how close an experimental result is in the value of the experimental quantity measured, right? I know that's a lot of reading, but say we, all right, how can I put this? So theoretically speaking, let's just say that we measure the length of a person, right? We got a computer to measure the length of a person. And the computer said that this person is 3 meters high, is 3 meters tall. No, we did an experiment and we used a meter ruler and we found out this person is 2 meters tall. Is that accurate?
Sir.
Go again?
No, sir.
Right. So it is not close, right? It's not really close to what the theoretical value is. So it's not accurate, right? If it was at 2.9 or 2.8, then we could say that it's a little bit more accurate. But at 2, that's too far, right? Precision, on the other hand, refers to how long the uncertainty in an experimental quantity is compared to the size of the quantity itself, right? I'll explain this as well, right? The uncertainty, right, is, all right, let's just read this and then let's explain it. So in quoting an uncertainty, there is a standard format which is normally followed. First, find the count or the smallest printed division of the measuring device. All right, now we were using a ruler, right? And we said that this person is 2 meters tall. All right, 2 meters tall. Now on a meter ruler or we use a tape measure in this case. Let's use a tape measure. On a tape measure, the smallest increment is actually 0.1 centimeters, right? So if you can remember, on your meter ruler, you have this big guy, then small, 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 then another medium size, that's for the half mark, then another set of small increments, and you have another big one. So you have 2 big ones, you have a small one in the middle here, which represents half mark, and we do the same thing. And then 1, 2, 3, 4, right? So look something like this. The smallest increment would represent your uncertainty, right? So we don't know the exact reading, but we know that it falls in between, right? The smallest. All right, so let's just say this is 0, and this is 1, and this is 2. What is this value here? Say our reading stops here.
1.5.
Right, so 1.5. Now our reading is at 1.5. Are we all seeing that? All right?
Yes, sir.
All right, so we know that it falls in between 1.4 and 1.6, but we don't know exactly where, right? So we make an estimate and we say 1.5 plus and minus 0.1 centimeters, right? So we don't know exactly where this is. Please let me know if I get it. Whenever we're doing labs, right, you have to state your uncertainty. It's not like CSEC. Moving forward, right, even if you're doing any chemistry or any form of measurements, you'll have to state your uncertainty, right? We see that it's 1.5, but we have to state our uncertainty because there could still be errors such as parallax error. We could be reading, right, from a different angle, right? We could be reading from a different angle, and it could not be, it's possible that it's not correct, right? Suppose we're reading from this angle, right? This angle here. So we see the angles can be very small, but we have to ensure that we place our uncertainty because we're still not fully sure, right? So say you are measuring the length of the object with a meter ruler, and the meter sticks, the smallest division is 1 millimeters, right? 0.1 centimeters. Hence, we have to be able to measure with plus or minus 0.1 centimeter accuracy. All right. So in the next session, I think we can do we'll try and do more calculations as it regards uncertainty, and for your your measurement to be precise, right? The uncertainty has to be small compared to the size of the measurement. All right, that's how we know a measurement is precise. You cannot have, say this was 1.5, and then you're going to tell me that the uncertainty is plus and minus 0.5, right? That is not precise. So we have to say something like plus and minus 0.1, right? That is very precise. Are we all clear on precision and accuracy?
Yes, sir.
All right.
Yes, sir.
All right. That's good. So consider the length of the object is 6.8, right? Then the length measured can be recorded as 6.8 plus and minus 0.1. That's your uncertainty. Whenever you're making any form of measurement moving forward, you have to place an uncertainty there. Plus and minus means that the value of L, even if you know, even if it is known by the experimenter, right? It most likely falls between 6.9, right? 6.9 and 6.7. So 6.8, we know that it's 6.8. We look on it again, we read it again, right? And we ask somebody else to come and say, look on this measurement. We know that it's 6.8, but we have to place an uncertainty. All right. Okay, so the standard free fall acceleration near the Earth's surface is 9.8, right? Agreed? Have you ever seen this before?
Yes, sir.
All right.
Yes, sir.
9.8 meters per second squared. Two students set out separately to measure the acceleration due to gravity and found that student A found that G is 9.81 plus and minus 3.00 meters per second squared. Student B found that G is equal to 8.44 plus and minus 0.01 meters per second squared. Comment on precision and accuracy of each student. I hear someone is ready to answer.
Morning, sir.
Oh, morning, Tevin.
Can I leave? One minute, miss. Can I leave? Internet problem.
All right, no problem. The class has been recorded, so that will be posted on Google Classroom. All right. All right. So for the rest of the time, let us talk about this. Which one is accurate, or which one is which one is accurate?
Student B.
9.81, sir.
All right. So somebody saying 9.8. Somebody saying student B. Why 9.8? I believe that was Whittingham. You said 9.8. Ms. Rochelle, you said 9.8. Why 9.8 is more accurate?
Mm,
All right. All right, the other person that says student B, right? I believe that was Miss Chris. I don't want to call the names. I am bad at
Chrysanthia.
names. Cassandra.
Mm-hmm.
Yeah. So you said student B. Why student B?
Because your uncertainty is something like less.
The answer is what?
Say uncertainty is something less.
All right. So she said that the uncertainty is much less, right? But does that really say whether it is accurate or not? Let's go back, right?
No.
No, because it's not close to the original.
All right. So that's good. So accuracy refers to how close an experimental result is in the value of the experimental quantity, right? So that's very important. The experimental result has to be close, very close to the actual experimental quantity measured. So experimental quantity is 9.8. They proved this already, right? This is a proven fact. That is 9.8. And student A got 9.81. So it has to be more accurate than 8.44. We all agree?
Yes, sir.
All right. All right. You all agree 9.81 is much closer than 8.44. No, which of the two is more precise? No, which of the two is more precise?
B,
All right. So student B is more precise. Why?
because it has a less uncertainty.
So it has a smaller uncertainty of 0.01. Are we all seeing that? Any questions so far? All right, I'll take that as a no. So we move on now to error propagation. All right. So we won't be able to finish this now, right? We'll have to come back after the break because we have 5 minutes left. But error propagation is simply the process of determining the uncertainty of an answer obtained from calculations. Now, you might come across, say, all right, let's go back here. You might have used a ruler. Remember moments, right? Anybody remember moments? And the formula for moments is, anybody remember the formula for moments again? Force times distance, right? Force times distance. Now, in order to calculate the distance, we use the meter rule. And we said that the uncertainty of the meter rule is 0.1, right? And we used a top pan balance to measure the mass, and then we calculated the force from that. So let's go back a few seconds. Force equals mass times acceleration due to gravity, right? So we use a top pan balance and we found the weight or the force, right, exerted on the for the moment. Now we need the uncertainty to present in our answer, right? So we have to use error propagation to determine the uncertainty of this particular guy here. or the final answer of moments, right? Because we could have found this from the ruler. We could have used the ruler, but in this case, we have to do calculation. So usually we cannot make a direct measurement of the quantity we are interested in, but we must measure another quantity or quantities and calculate desired quantities from them. All right. So we cannot really use let me get this marked up, right? So we cannot really use a system, or we probably don't have the equipment to measure the force exerted on a moment or the force exerted on a system, right? We have to use other quantities such as the force, and we have to use the mass, and we have to use the distance to calculate the moment. So in order for us to find the uncertainty for that, we have to use error propagation. All right, so we'll pause here because we have 2 minutes left. We can't really go into it as yet. We have 2 minutes left. Let us go for lunch, and then we meet back here 12:30. All right,
Sir,
question?
sir, I can post the first part I brought and we
Yes,
can
I usually do that.
catch up.
I usually post the class and the notes. All right,
Yes, sir.
all right. All the best.